I will determine the symmetries of the normal modes of the vibration of a water molecule. And let's say this is the z direction, this is x direction pointing towards the camera, and y direction is this, and we have oxygen here, and we have 100 here, 100 here. And let's define this plane that contains these three atoms. Let's define this to be sigma v prime. What about sigma v? This is sigma v. Okay, that bisects the H2O molecule, and over here that shows the rotation operation. Here's the character table. E means doing nothing, C2 means rotate the molecule by 180 degrees. Sigma v is the reflection with respect to, again, this symmetry plane, and sigma v prime is the reflection with respect to this symmetry plane. So we have four different irreducible representations: A1, A2, B1, B2. And A means, well, it's symmetrical with respect to rotation. B means it's anti-symmetrical with respect to rotation. And we have 1, 2. So if you look at 1 and 2, 1 means it's symmetrical with respect to the reflection with respect to sigma v, and the 2 means it's anti-symmetric if we reflect this molecule or the motion with respect to sigma v. Again, 1 means symmetrical with respect to this sigma v operation. 2 means anti-symmetrical with respect to the sigma v operation. And now we'll have to determine the symmetries of all 9 possible motions. Why 9 possible motions? It's because we have 3 atoms, and for each atom there's x, y, z coordinates. So we have a total of 9 coordinates. So we can have this oxygen moving in the x direction or y direction or z direction. Similarly, we can have this hydrogen moving in the x direction, y direction, and z direction. So we'll have to look at the 9 motions separately. So first, we'll look at this oxygen atom, and let's say this oxygen is moving in the z direction. Okay, so I'm going to use a notation here. It's moving in the z direction, so I'm going to say oxygen moving in the z direction. This uppercase E means doing nothing. That does not change the direction of the motion. It does not change the position of this. Again, we're talking about this arrow here, which stands for the motion of the oxygen in the z direction. So there's no change here. And if you rotate this arrow about the C2 axis, there's no change. If you do a reflection with respect to sigma v, this one, or sigma v prime, that one, there's no change, no change. Now we're going to look at this, the motion of the oxygen atom in the y direction. So we're looking at a different arrow here. This is the y direction. This is z, this is y. And then if you do nothing, there's no change. The vector, this y vector, stays in its original position, and that the direction remains unchanged. And then if we do a rotation of this vector, the direction changes. Therefore, we put a -1 here. And how about the reflection with respect to this symmetry plane that bisects the water molecule? That will change the direction of the y vector. So we put -1 here, and last we have sigma v prime, because sigma v prime contains this vector. Therefore, the reflection of this y vector with respect to sigma v prime does nothing. Again, the vector stays in its original position, and also the direction remains unchanged. And then we look at the motion of this oxygen atom in the x direction. So it's a little bit hard to show the x direction because, well, it's pointing towards the camera, it's perpendicular to the whiteboard, and this is the x direction. You have to imagine this x vector. And again, there's nothing here. And when we do a C2, this x vector will rotate, and it's going to point to the opposite direction, therefore a -1 here. And now let's look at sigma v operation, because the sigma v symmetry plane contains this vector, and then therefore there's no change. Sigma v prime, again, you have to imagine this x vector perpendicular to sigma v prime, and that will change the reflection with respect to sigma v prime will definitely change the direction of the motion of the oxygen atom in the x direction. So we're done with the oxygen atom. Now hydrogen atom. We'll look at this hydrogen atom on the left. If we again draw an arrow here, that's the motion of this hydrogen along the z direction. If we do nothing, well, again, the vector stays in its original position and the direction remains unchanged. What about the rotation, C2 rotation? Look, if we rotate this arrow about the z-axis, that will move this vector out of its original position. And that means it's neither symmetrical nor anti-symmetrical, so we cannot put 1 here, nor -1, we'll put 0 here. What about the sigma v symmetry plane? Again, if you do a reflection with respect to this sigma v plane, this vector will move away from its original position, therefore put another 0 here. How about sigma v prime? That's just simply 1 because sigma v prime contains this z vector of the hydrogen. And then we're going to do the hydrogen atom moving in the y direction. So we're going to draw the arrow here. All right, so if we do nothing, the character is 1. If we rotate it, it's out of the original position, that's 0. If we do sigma v, again, it's 0. And if we do sigma v prime, it's 1. How about the x direction? The x direction, again, is pointing towards camera. It's perpendicular to the whiteboard. It's perpendicular to sigma v prime. Again, if we do nothing, it's going to be 1. If we rotate this x vector about the z axis, it's going to be just like this, okay? It's moved away from the original position. It's neither symmetrical nor anti-symmetrical. That's why I put 0 here. And also for the reflection with respect to sigma v, again, that will move this x vector to here, from here to here. Again, it's neither symmetrical nor anti-symmetrical if the vector is moved away from the original position. How about sigma v prime? Okay, again, this is your z. If we do a reflection here, it's again, my hand is now sigma v prime. If we do the reflection of this red marker with respect to the sigma v prime, this vector will stay in the original position, but the direction changes, so it's anti-symmetric. So we're done with the hydrogen atom on the left. However, there's another hydrogen atom on the right. Fortunately, this the second hydrogen and the first hydrogen have the same characters. So basically, we're going to just multiply everything by 2 here. And if we do that, I'm going to just change every 1 to 2. So it's 2, 2, 2, 2, 2, -2. And then we're going to sum it up. And let's look at this E operation. That means doing nothing. 1, 2, 3, and then over here, 2, 2, 2. You sum it up, you get 9. And then 1, -1, -1, and 3 zeros, you get -1. And then you sum this up, 1, 1, -1, you have 1 here. And this guy is 1, 1, -1, and then 2, 2, -2. The sum of this 6 characters is 3. So again, over here, this row tells you the sum of the characters with respect to these 4 different operations. It's not surprising to see that you know, this E means doing nothing, and then you have a total of 9 here because you have 3 atoms. For each atom, there are 3 possible motions, a total of 9 different motions, and nothing changes here, so that's why it's 9. But the other 3, I mean, you have to kind of just look at the motion of each atom one by one in each of the 3 dimensions, one by one, and you have the sum here. So I'm going to put the sum here. All right. And then we'll look at the translation of the entire molecule. There are 3 possible translations in the x direction, the y direction, and z direction. And we're going to look at the rotation of the molecule. And also there are three possible rotations. The rotation about the x-axis, y-axis, and then z-axis. And three translations, three rotations. And we have determined that if we're looking at individual atoms, there are 9 possible motions. 9 possible motions in total, minus the 3 translations of the molecule, minus the 3 rotations of the molecule. The remaining 3 motions are concerted vibrational motions. Oh, they are called normal modes of vibration. So how do we determine the symmetries of the normal modes of the vibrations? We'll have to determine the symmetries of the translations. So again, I'm going to draw the same picture here because this one is a little messy. This is sigma v prime, and there's sigma v perpendicular to sigma v prime, which also contains C2. Now we're going to look at the translation of the molecule. Let's say the translation of the entire molecule along the z direction. So I'm going to draw an arrow here. So this is translation in the z direction. We're going to determine the characters of this translation in the z direction. Again, we look at this E, that means doing nothing, so we have this character here, E2, C2, sigma v prime, so we're going to say it's symmetrical. C2, we're going to rotate this red vector about the C2 axis, and it does nothing, sigma v, nothing, sigma v prime, nothing. And then we're going to look at the translation of the entire molecule in the y direction. So this is the y direction. Okay, and then y direction. Again, this is the translation of the entire molecule represented by this arrow. So if we do nothing, oh, I'm sorry, this is just E, that means doing nothing. And it's symmetrical, it's not changing anything, but if we rotate this, the direction of the translation changes. If we do the reflection with respect to sigma v, this translation in the y direction will change. Sigma v prime, no change. How about the x direction? What about the x direction? Let's just imagine this molecule, the entire water molecule traveling in the x direction. So this vector represents, this red marker represents the motion of the entire water molecule. And again, this is 1 because it means doing nothing. If we rotate this vector about the z axis, again, it's doing this. It's going to change the direction of the vector. So -1 here. How about sigma v? Because sigma v contains this x vector. And again, we put 1 here and -1 here. All right, so those are the 3 translations. Now we're going to look at the 3 rotations. See, sigma v prime. And we're about to do the 3 rotations. First, the rotation about the z-axis. This is the notation of the rotation about the z-axis. Again, if we are doing nothing to this rotation, so I'm going to use r sub z for the rotation about the z-axis. If we do nothing, it's symmetrical. If we rotate this circular arrow by 180 degrees, that does not change the direction of the arrow. So it's still +1. All right? And then we're going to do reflection here. So we're going to do reflection. So basically, if we are looking at the reflection of this circular arrow with respect to sigma v, you have to kind of imagine over here, okay, over here, that's the symmetry plane, and what's the mirror image of this guy? The mirror image of this guy, again, it's in black right here. It actually changes the direction. It changes the direction of the arrow. So, and then we look at sigma v prime. We look at the sigma v prime. And what happens if we do a reflection of the rotation about z with respect to this sigma v prime, it changes direction. So it's very interesting here. And then we're going to do the rotation about the y-axis. This is the y-axis, and the rotation is a little bit hard to draw. It's going to be like this. Okay, it's this motion. Okay, and this rotation is on the xz plane. It's about the y-axis. Therefore, this rotational motion occurs on the xz plane. So if we do nothing, it's going to be just a 1. If we do a rotation of this motion, again, we're going to rotate this motion 180 degrees. So you'll have to kind of imagine a arrow here. It's pretty hard to make an arrow with just a few pins. So let's say, let's just imagine this is a circular arrow, and then we're gonna about to kind of rotate this. Okay, and over here when I look at this, and assuming this is the positive direction, I'm looking at this. Again, we pretend it's a circle. This is counterclockwise, I believe. This is counterclockwise. Again, it's doing this. And then if we rotate this 180 degrees, again, we'll have to imagine this is not a triangle. This is a circle. And this is, again, this is the positive direction. So we're looking at clockwise. So we changed its direction. It's easy to determine the symmetry of this circular arrow with respect to sigma v, because the sigma v symmetry plane contains this arrow, so nothing changes. And then finally sigma v prime. Sigma v prime bisects this. So again, let's say we have, imagine this is a circle, and then we're gonna just do a reflection with respect to this plane, and the direction changes. Over here, this is counterclockwise. Over here, it's clockwise. So we have -1 here. And similarly, we do the rotation about the x-axis. Actually, this is easier now because it's possible to draw the circular arrow here. It's just a circle about the x-axis. This dot is the x-axis. So this is y, and this dot, I'm going to put a plus sign here, and to indicate it's an x-axis. And then if we just look at this rotation, again, it's a circular arrow, and if we do nothing, it's going to be 1. If we do a C2 operation, basically we just have this circular arrow rotated 180 degrees. We will change its symmetry. And then the reflection with respect to sigma v. This is sigma v. Apparently, when we look at the mirror image of this arrow with respect to this symmetry plane, it changes. The direction changes, so put a -1 here. Okay, and finally, the sigma v prime. This sigma v prime that contains this circular arrow, so nothing changes if we do a reflection with respect to sigma v prime. So, and we are going to sum it up, the translations. The sum of the characters of the 3 translations: 3, -1, 1, 1. Well, again, it's just, you sum it up, it's -1. You sum it up, you get 1. You sum this up, you get 1. 3, -1, 1, 1. Those are the characters of the 3 translations in the 3 directions. Similarly, we sum it up over here. Okay, 3, that's the sum of the characters of the 3 rotations. And over here, there's a -1, -1, -1, -1, -1, and -1. Okay? So we determined the symmetries of the 3 rotations, and the 3 rotations translations of the entire molecule. All right. So this is 9 motions. We have 9 minus 1, 1, 3, all 9 motions. And then we have this guy, we have this guy, we have 3 translations, we have 3 rotations. So I'm gonna just put this to here, 3 plus 3, that's 6. And we're gonna just subtract that, okay, subtract that. Subtract 6. If we look at this, -1, -1, so -2 here, we're gonna use -1 minus -2, okay? And then 1, -1 is 0, 1, -1 is 0. So basically we're doing a subtraction here for each of the 4 operations. And this is the E operation, this is C2 operation, this is sigma V operation, and sigma V prime operation. 9 minus 6, I got 3, minus 1 minus minus 2, that's just 1, and then 1 minus 0, that's just 1. And then 3 minus 0, that's again 1. We're not done yet. We know that the sum of the characters of the 3 normal modes of vibration will be 3, 1, 1, 3. Again, 3, 1, 1, 3 will be the sum of the 3 of the 4 rows, and we may have the same row twice. So how do we decide whether this is kind of the sum of A1, A2, B1, or maybe it could be A2, B1, B2, the sum of these 3 rows, or it could be even, the sum of this row plus 2 times the second row. So who knows? But there's an easy way to determine what are the 3 individual normal modes of vibration. Again, it's just mathematics. Okay. What we need to do is, again, this is 4 different operations. No operation at all, rotation, sigma V prime, okay? So now we're gonna determine whether we have a A1 normal mode. So this means the number of A1 normal mode is equal to. All right, again, it's just mathematics. 3 times 1, 1 times 1, 1 times 1, 3 times 1. We do this in a consistent manner. We have this E, uppercase E here, that's 3. This is 1, so 1 times 3 plus 1 times 1, 1 times 1, and then 1 times 3. Right, and we get the sum, and after we get the sum, we need to divide this by the order of this character table. Basically, just the number of rows and number of columns. 3 plus 1 plus 1 plus 3, that's 8 divided by 2. Hey, we have 2 normal modes with A1 symmetry. Okay, number of A2 normal modes. Again, 3 times 1 here. Oh, 1 times 3, 1 times 1. Negative 1 times 1, negative 1 times 3. 0. We have 0 normal modes with A2 symmetry. We're going to look at the B1. 1 times 3, that's 3. So I'm not going to show the multiplication again. Minus 1 times 1, minus 1 times 1. Negative 1 times 3 divided by 4, again, 0. B2. Now we can even predict, since we have 2 normal modes with A1 symmetry and we have 3 possible normal modes for vibration. Again, you have 9 possible motions minus 3 translation minus 3 rotations. We should get 3 vibrations, but why don't we anyway do this calculations consistently. 1 times 3, that's 3. Minus 1 times 1, that's minus 1. Minus 1 times 1, that's minus 1. And 1 times 3, that's plus 3. So if we do the math, it's just 1. Again, in the end, I'm going to use a different color. the number of normal modes with A1 symmetry. 2. We have 2 normal modes with A1 symmetry. How about B2? We have 1 normal mode with B2 symmetry. How about A2? 0. B1, 0. We're done.